Welcome to EPG Pathshala for Computer Science. So, we are looking at computer networks. So, topic we will be looking at today is on queuing disciplines as applied in computer networks for packet scheduling and for providing QoS at the routers. So, we will look at scheduling and then we will also look at the different queuing disciplines that are employed. So, we will look at the Fifo, fair queuing, and we will look at weighted fair queuing. So, what is the need for a scheduling discipline? That is the first question that we need to answer. So, why do we need a non-trivial scheduling discipline? So, remember that per connection delay, bandwidth and loss are basically determined by the scheduling discipline. Okay. So, we need a effective scheduling discipline. Okay. We need a scheduling discipline is definitely a known fact. How effective it should be is important because these three primary performance related parameters are directly affected by the scheduling discipline. So, you could allocate different mean delays to different connections by its choice of service order. Okay. So, that is one important aspect. Second thing is you can allocate different bandwidths to connections by serving at least a certain number of packets from a particular connection in a given time interval. So, you can affect the bandwidth. Similarly, you can allocate different loss rates to connections by giving them more or fewer buffers or choosing to drop packets from certain flows. Right. So, you can see that the scheduling discipline that you use by appropriately doing proper allocations can affect the delay, bandwidth and the loss. So, this becomes one of the important aspects of our QoS techniques. Okay. So, if you look at packet scheduling, the objective you can say of packet scheduling is to provide a mechanism to divide the bandwidth and guarantee that each flow can get the allocated resource. So, that is the overall objective of packet scheduling. Now, what are the issues that we need to look at when we are doing this? Okay. First thing is we need to have a mechanism which is simple to implement. Simplicity of implementation is important because now this is something that will be happening for every packet, right. So, we need to have a simple mechanism which is implemented quite well and it has to be fair, right. Fairness in terms of different flows getting the required bandwidth, right, and other parameters. So, that is important. We already seen when we talked about queuing and talked about QoS that isolation of flows is important, right, because we need to be separate one flow from another flow. A misbehaving flow should not affect the performance of another flow. Okay. And we would like to have low end-to-end delays, good utilization, scalability, and whether we need to have a work conserving or a non-work conserving kind of an approach. We will look at what we mean by this shortly. So, in general you can say that a scheduling discipline must satisfy 4 requirements. So, as I said, ease of implementation. So, pick a packet every few microseconds. So, we need a scheduler that takes order of 1 and not order of n time, right. Fairness and protection, this is for best effort connections. So, you normally if you use something like a Fifo, a first in first out kind of scheduling mechanism, it does not really offer any protection because one misbehaving connection can increase the mean delay of all the other connections. Okay. So, round robin scheduling is an option, but again there are certain things that we need to consider in terms of how that is done effectively. Okay. Another requirement is performance bounds. So, the your common performance parameters of bandwidth, delay, jitter, loss and so on. Depending on either deterministic or statistical bounds, we need to make sure that the scheduling discipline provides the or guarantees those performance bounds. Another is ease and efficiency of admission control. That is, when a new connection is to be admitted, you have to make sure that you are able to meet the new connection's performance requirements and bounds without affecting the performance of existing connections. So, that is another requirement. So, broadly you can say that these are 4 requirements for a scheduling discipline. Okay. And when we talk of designing a scheduling discipline, there are 4 principal degrees of freedom that we normally look at, right. One is the number of priority levels. Second is whether each level is work conserving or non-work conserving. Third is the degree of aggregation of connections within the level, and fourth is service order within a level. Okay. So, how do I actually provide a scheduling, right? How do I choose my scheduling discipline? How do I design my scheduling discipline? So, when you talk of that, these are parameters that we normally consider. Okay. And each feature obviously comes with at some cost. So, we need to have a judicious trade-off that you need to be looking at. Okay. So, for a small LAN switch, okay, for instance, if it's a very small network. So a single priority FCFS or first come first served or FIFO scheduler, or at most a 2 priority scheduler may be sufficient. But if you look at a very heavily loaded wide area public switch kind of network, where you may have non-cooperative users, then we need a more sophisticated scheduling discipline. Okay, so it depends on the situation. So how much are we willing to pay? That's also an important aspect. Okay. So we talked about is work conserving versus non-work conserving. So what do we mean by work conserving? A work conserving scheduler is idle only when there is no packet awaiting service. So if there is a packet awaiting service and there is resource available, it will be done immediately, it will be scheduled immediately. Okay. So normally what you would think is, that is what I would like to do, right? I would like to always, the moment something is idle and I have work to do, I will just allocate that work and be done with it. Okay. So why would I even look at something called a non-work conserving discipline or a scheduler? Because when you say non-work conserving, it means that even if there are packets to serve, it may be idle. So why would I want this kind of a situation? You may want this non-work conserving scheduler in situations where you need to kind of control the traffic that is arriving at some downstream switch. Okay, so you want to make the traffic which is arriving at a downstream switch more predictable. Okay, so you may not want to send all the packets that you have already serviced or that you have accumulated immediately to the downstream router. Okay, you may want to delay it. Okay, you want to make it predictable at that end. Okay. Similarly, it also reduces the buffer size necessary at the output queues and the delay jitter that is experienced by a connection. Because if you are not just sending it as soon as it comes, but sending it at a regulated rate, okay, that obviously helps. Okay. Similarly, it allows the switch to send packets only when the packet is eligible. So you can kind of look for the eligibility of the packet before you are sending it out. Okay. So for example, if the k+1th packet on a connection A, okay, becomes eligible for service only I seconds after the service of the kth packet, so then the downstream switch receives packets on A no faster than 1 every I seconds. So you are kind of regulating the flow so that your the switch on this connection can effectively handle the flow when it comes to it. Okay, so you may want to go for a non-work conserving discipline also, right? So we need to choose between work conserving versus non-work conserving. Okay. So if you look at these different scheduling mechanisms that have been proposed, okay, that have been looked at, one of the first ones that people have always used is the first in first out scheduling, which is very simple. You just send packets in order of their arrival, okay, to the queue, and when a packet comes in, there are free buffers available, packets are queued here, they come and sit in the next free buffer space, and the one which is the front of the queue is the one which is next to be transmitted. Okay. So if the packet arrives to a full queue, what do we do? Which one do we discard? So here we talk about discard policies. So a tail drop would mean that you drop the arriving packet, the one which is at the tail. A priority would be based on some priority basis, you could drop some packets, or you could randomly drop packets. Okay. So often we find that with FIFO, with the first in first out scheduling mechanism, tail drop is the one that is typically adopted. So when you have when it is full and a packet arrives, it is just dropped. Okay, you don't disturb the rest of the queues because very simple to implement. Okay. Of course, what we also have to remember here is that FIFO and tail drop are two separate ideas, right? Because this is a discard policy. Tail drop is a discard policy, FIFO is a scheduling policy. Okay, so it's not that these are part of one and the same, but normally they are used together. So that's the point that we are trying to make here. So advantage of FIFO is that it is very simple to implement, but the main disadvantage is that it does not discriminate between different traffic sources, because all the packets are just sent to one queue and they just sent in that order, in the order in which they have arrived. So it does not separate packets according to the flow to which they belong. Okay, this is one of the major disadvantages of FIFO. So another option that we have is the priority queuing approach. So this is basically a very simple variation of the FIFO. Only thing is we have multiple FIFO queues, one for each priority class. So what do we do when a packet comes in? You mark the packet based on its priority. It comes with a priority marking, and based on that priority marking that you have, you will put it into different queues, and then you will send packets out of these queues. And the order in which you send the packets out of the queues, the router will transmit packets out of the highest priority queue, okay, if that queue is non-empty. Only when that becomes non-empty, it will move to the next priority queue. So when that becomes non-empty, it will move to the next one and so on. Meanwhile, if there is another higher priority packet that comes in, obviously you will go back to servicing those high priority queues. Okay, so here you can provide, we have multiple classes and you are providing higher priority to certain packets. Okay. Within each priority, packets will be still managed in a first in first out manner. Okay. That is the approach that is used here. Okay. So for instance, so typically what will happen, the way it will be implemented is like this. When packets arrive, they are classified into belong to either high priority area or a low priority area, right. So they would put them in a high priority queue or a low priority queue, and so they wait at this queue, and from here you process the high priority queues first before you send the low priority queues. Okay. So if I have packet 1 coming in, so this is the packet in service, so it will depart at this time, right. If I have another packet 2 and 3 coming in meanwhile, they will wait. Now 2 is low priority, 3 is high priority, so the next one to go will be 3, right. So 3 will be the one that goes next, next is when 2 will go. Now if another high priority packet comes at this time, so that will be the one that gets scheduled immediately, right, and then a low priority packet comes and so on. Okay. So disadvantage of this mechanism basically is that it could lead to starvation, because if you have many high priority packets coming in, obviously they will keep getting serviced and the low priority packets will suffer. So it is not fair. Okay. So that is fairness is definitely one of the questions that arises in priority queues. So when you talk of fairness, the immediate thing that normally comes to our mind is a round robin scheduling. Okay. Because what do we do in round robin scheduling? You have multiple classes and you cyclically scan these class queues, sending one complete packet from each class if it is available, right. So this is what we will do. So for instance, if packets are arriving in this order, okay, 1 comes, I send out 1, okay, next let us say packet 2 comes in belonging to the same class, and then I have a packet 3 which comes in which belongs to a different class. So now already I have sent out 1, so which is the one that I will send out next? Next to go out will be 3, okay. Now, so 3 will be the one that goes next. Now the 2 which was there in the previous queue will be the one that is sent out, okay. So let us say another 4 comes in here, okay, so the next packet to go will be 4 because there is nothing from the other queue, right. So 4 will be the one that goes out, okay, and then after some time if a 5 arrives, that will be the one that is sent out and that is queued, okay. So this is our round robin scheduling. So what are the issues with respect to round robin scheduling? Of course, the advantage is that it is again simple to implement, but again, is it fair? Okay. Now I thought we went into round robin scheduling thinking it was fair, right, but what is it that would make it unfair with respect to the network scenario? Now remember that when we talked about packets getting scheduled and sent out, okay, packets could be of variable length. If all packets are of the same size, for instance this example showed all packets to be almost of the same size, but that is not going to be the scenario, right, in reality. So when packets are of different sizes, when you have variable packet lengths, by just sending larger packets, I can get a higher share of the bandwidth, okay. So if I want to do a fair allocation, you should also consider the packet length. So a simple round robin of 2 flows, one which has 1000 byte packets and the other which have 500 byte packets, if you take, you will find that the first flow will get 2/3 of the link's bandwidth, while the second flow will only get 1/3 of the link's bandwidth. So obviously it is not fair, okay. So we need to consider the packet length as well, okay. And you can have unfair instantaneous service rate, especially look at what will happen if a packet arrives just before or after a packet departs, okay. Just before a packet departs if it arrives, it may get scheduled earlier, right, or just after a packet departs it may have to wait longer, so that you have an unfairness in terms of instantaneous service rates also, okay. So this fairness is a very important question that needs to be addressed, okay. So how do you actually handle this fairness question? So at what granularity has fairness to be considered? Do we have to give flow wise fairness, or has to be connection wise fairness, or domain wise fairness? What is the granularity at which fairness has to be provided? That is one important question. And what if users have different RTTs, links, etc.? So should it share a link fairly, or it should be TCP fair? I mean, what exactly are we talking about? Okay. Actually, it is a very tough question to answer, okay. Typically we need proper design mechanisms, and it is not just policy based matters, and basically users use arbitrary granularity. So you need to have good mechanism of ensuring fairness. So if you take to understand this fairness problem further, so let us say we have a router here which has a connected by means of 1.1 Mbps network. So I have 10 Mbps here and 100 Mbps here. So what is fair allocation here? So do I say I have 1.1, so 1.1, so let me just divide this equally, no, 0.55 for this flow and 0.55 for this flow, okay. Is it fair allocation? Or would I say this is a 10 Mbps rate, this requires 100 Mbps rate, so let me give 0.1 Mbps to this and 1 Mbps to this. Is this a fair allocation? Again, these are questions that need to be understood. Okay. And what if another new flow comes in? I get another 0.2 Mbps flow that comes in. So what will be the fair allocation in this situation, right? So those are things that we need to understand. So in this fairness problem that is there, okay, one of the common techniques that is used in order to provide reasonable amount of fairness is what is called as the max-min fairness technique. So what max-min fairness does is, it's a very simple technique. What it does is, you just allocate the user with the small demand whatever it wants. Okay, if I have users with small demands, give them whatever they want and evenly divide the unused resources to big users. Okay, so formally what this will amount to is that the resources will be allocated in terms of increasing demand. So you first allocate resources to the person who has the least demand, then you allocate the person who has the next highest demand, and so on. Okay. So no source will get a resource share which is larger than its demand. Okay, you will never give it more than what it needs. Okay, that is one very important aspect. So you won't over provision. And sources with unsatisfied demand will get equal share of the resource. So whatever is left over, that everybody else will share. Okay, so this is basically the essence of this max-min fairness that we have. What is the max-min fairness algorithm, right? How do we actually do it? So let's say we have n flows which share a link of rate c. Okay, if flow f wishes to send data at a rate of w of f, okay, its wish rate, and let's say it has to be allocated a rate r. How do we allocate this r? That's the problem. Okay, so what we do is, you have different flows. So you first pick the flow with the smallest requested rate, and now you take your capacity c, divide by n. If your wish of this flow w of f, okay, is less than c by n, then you set its allocated rate r to w of f. You give it whatever it's asked for, okay, because it is taking less than c by n. Okay, c by n is equal share for all. It is having less than that, so you allocate that to it. If your wf is greater than c by n, then you set the allocated rate to c by n. It only gets the equal share, okay, c by n. Now you set n is equal to n minus 1, right, and then c, you subtract whatever you already allocated, c minus rf from c, and then if you are not exhausted all the flows, go back and keep picking up the next flow which has the next smallest requested rate, and proceed in this manner. Yeah, so we'll take a simple example. So if you look at this, so let's say I have WF1s of 0.1, 0.5, 10 and 5, okay, the overall capacity is 1. Okay. So what will happen, round 1, you first need to pick the one which has the smallest requirement. Smallest wish is for 0.1, okay, it's basically in this 0.1, 0.5, 5 and 10 will be the order. So 0.1 is the lowest request, so I'll set RF1 to 0.1, because if I take 1 and divide by 4, I will actually get 0.25. So 0.1 is much smaller than that, so the first one will get 0.1. Now the rest of the available bandwidth, 0.9 is divided by 3, right, and that 0.3 is less than WF2. So therefore WF2 will get 0.3. Similarly, RF, the third Q also will get 0.3 of the bandwidth, and fourth also will get 0.3 of the bandwidth. Okay, this is basically how the maximum fairness will. So the one which has the least gets its full bandwidth, the rest of them share the available bandwidth. Okay, that's the maximum fairness scheme. Okay. Now what's important with respect to maximum fairness is that it will definitely converge to some alpha such that flows which have an offered load which are Ra which is less than alpha will definitely get Ra, and flows which have load greater than alpha will definitely get alpha. Okay. So that's the basic point that we have to understand with respect to maximum fairness. So how do you exactly provide this kind of a maximum fairness in a real situation? Okay. There are some kind of approximations that are used, or some kind of implementations of this that are used. One is called as generalized process sharing, which actually tries to provide something like a fluid fairness, okay, and it does it by kind of doing something what's called as a bitwise round robin among all queues. So we look at how these things are done. So this generalized process sharing is a fair queuing technique, okay, which tries to provide something which is very close to maximum technique using based on what is called as the fluid model. So let's understand what we mean by this fluid model. So when you have, so let's say we have different flows, fluid flows, okay, and if there are 3 different flows, okay, they will actually share, they will simultaneously be using the using whatever pipe is there. If I have one pipe through which 3 different flows have to be sent, each can be allocated separate regions, so they could go simultaneously. So if I have A1 going on flow 1, B1 on flow 2 and C1, So A1 will use up to this time, then A2 over here, A3 will use up this time and so on. So A1 will get over at this point of time, B1 will get over at this point of time, C1 at this point of time and so on. Now if you look at the same thing with respect to packets, obviously we cannot have 3 packets going simultaneously in the network, right, because it will be only one packet at a time, right, you can't have it. So what we can actually do in order to approximate this is that, because obviously cannot be directly implemented on networks, but this is the kind of fair model that we would like to achieve. So what we do is, you look at the finish times in this, okay. If you can schedule your packets such that they will finish in this order, then that itself will amount to a fair queuing or an approximation to this, or getting close to this fair queuing, okay. So I have, like you can see that here C1 will be the one to finish first, so that should be the packet that goes first. Next would be A1, so that will be the one that go first. Next would be B1, right. Next to go would be A2, that finishing first. Then would be C2, okay. Then will be A3, and then will be B2, C3 and so on, okay. So this is what we would like to do, okay. So how do we do this? So this is done by means of what is called as fair queuing technique. So what we need for fair queuing is, you need to do a, ideally what we need to do if you are looking at it from a packet point of view is that, if I could send one bit from each flow, right, that will give me almost a model which is similar to this fluid model, okay. So I want what is called as bit by bit round robin technique. So router transmits a bit from flow 1, then a bit from flow 2, and then from next flow and so on. Now obviously this is not practical because we cannot interleave bits from different packets. So what the fair queuing mechanism does is, it just tries to simulate this behavior, okay. Okay. Let us look at the key concept in fair queuing. So what we do is, when a packet arrives, you first determine when this given packet would finish transmission if it were being sent using a bit by bit round robin approach. That is, if we were using bit by bit round robin, what would be the finish time for this? Okay. Determine that, and we use this finish time to sequence the packets for transmission. This is the key idea that is used, okay. So what actually happens when you have multiple flows, you can look at it as doing it in round robin fashion with a clock which is ticking when a bit from all the active flows is transmitted. So this clock basically is ticking with respect to a round. That is, when you finish one round, one clock tick is over. Now why would we want to count this way? You can see that this is a very important aspect to understand this. That is, the number of rounds to send a packet is independent of the number of active flows, okay. So this is very useful to understand it this way, because if I have, because what we are interested in is, if there are 4 flows in one round and 3 flows in another round, we are not worried about that. We are more worried about in which round it will complete. That gives us a better way of implementing this fair queuing concept. So we look at it in, so the finish time is done in terms of a virtual clock, which you can look at it as the round at which it will finish, okay, which is dependent only on the number of flows that you have, okay. So how do we do this? Okay, so send the packet with the smallest finished round number, that is what we do. So this will approximate the bit by bit RR. Now is this exact? This is also not exact, okay. It is not exact because you cannot have preemption. That is, let us say I have sent out a packet is currently being transmitted. Another packet comes which actually has a finish time which is smaller than the one that has just been sent out. Now what will happen? Ideally this should have gone out first, but the previous packet has already been transmitted. So I cannot preempt it, right. So in which case the order will be a little different, but at least you will get close to the required fair queuing that we are talking about. So how do we approximate this bit by bit round robin? What do we actually do? So let us take a single flow. So let us say Pi is the length of the packet I, Si is the time when the router starts to transmit packet I, okay. Now let Fi be the time when the router will finish transmitting packet I, okay. Now clearly Fi is equal to Si plus Pi, okay. So this start time plus the length of the packet. Assume that Pi is normalized, it is a normalized length of packet with respect to time, in terms of time. So we know that Fi is equal to Si plus Pi, but how do I determine this Si? That is what I need. So now when I start transmitting the packet depends on whether the packet I arrived before or after the router finishes transmitting the packet I minus 1 for that particular flow, the previous packet, right. So if Ai is the time at which the packet I arrives at the router, your Si is going to be either Fi minus 1 or A, maximum of these two. That is, If ai was greater than fi minus 1, that will be chosen. If fi minus 1 is greater than ai, that will be chosen, right. So you can say your fi therefore now is si plus pi, where si is max of fi minus 1 comma ai plus pi, okay. So for each flow, therefore you calculate the fi like this, and this fi is treated as a timestamp. So the next packet that you need to transmit is always the packet which time, the lowest finish time. So that packet should finish transmission before all others. So that's the idea. So the way it will be done is the packets will come in, right? They will be, you will calculate si and fi and you will enqueue them, okay. So case 1 is if packet arrives to a non-empty queue. So then si is set to fi minus 1, right, because something is already in transmission. So si will be set to fi minus 1. Case 2 is a packet arrives to an empty queue, okay, then si is set to r of t naught, that is the time at which it is arriving, okay. So in both cases fi is equal to si plus pi, and your r of t is a monotonically increasing function with t, okay. So therefore you will find that departure order is same as in t, okay. This is typically what you will see, okay. An example to understand this. So let us say I have calculated finish times for 2 flows, flow 1 and flow 2. There are 2 packets come in here. One has a finish time of 5, this has a finish time of 8. This has a finish time of 10. So what will be the order in which they go? The one 5 will be the one to go out first, next will be the 8 finish time packet, next will be the 10 finish time packet, okay. Now let us look at a scenario where something is in progress, okay. So let us say for instance, flow 1 is arriving, okay, and flow 2 is transmitting at that time, okay. If flow 2 is transmitting at this time, now what will happen? Since this is already being transmitted, even though this has a smaller finish time, this has to go after this, okay. So this will go first, then that will be go next, okay. So you cannot preempt a packet which is being transmitted. So that is what we understand from this, okay. So another improvement on this fair queuing is a weighted bit by bit fair queuing. That is, here in fair queuing we allocated equal weights to all the queues. So instead we can also have different weights given to different queues. For instance, if I have weights of 0.1 to this, 0.3 to this, 0.3 to this and 0.3 to this, what I would like to do is I would like to transmit different number of bits from each of these flows. So these 3, therefore if you look at this example, if I transmit 1 bit from f1, I would transmit 3 bits from f2, okay, because this has 3 times its weight. Similarly f3 also I will transmit 3 bits, f4 also I will transmit 3 bits, then I will go back to transmitting 1 bit from f1, right. So this will give me a weighted fair queuing mechanism. So how do I do this? Again very simple, similar idea as FQ is done, fair queuing is done. Only thing is now in calculating your packet, the time taken to send out the packet, you divide it by Wi, okay, because it has, so the packets which have a higher weight will finish faster, okay. So you calculate your SI based on same max of Fi minus 1 comma Ai, Fi is set to Si plus Pi by Wi. Now you choose the one that has the lowest Fi and send them out in the same manner. So otherwise the idea is very similar. So this is an example of WFQ in operation, the weighted fair queue. So we are showing different flows are shown with different IDs, okay, your packet ID and the queue length is given. So given that these flows have weights of 0.1, 0.2, 0.3 and 0.4, based on the packet length we calculate the finish time, okay, or Fi or virtual finish time as it is called. So we calculate the finish time. When you calculate the finish times, you find that this has 2000, 4000, 6000, 8000, 200 divided by 0.1. So this will be 200 divided by 0.2, right. So you will get 1000 and so on, okay. So you get these different. Now based on these finish times, we need to send the packets out. So what is the packet that will go out first, right. So if you look at that, right, the one which has the lowest here will be the packet number 12, okay, with which has a finish time of 500. So if you look at the finish times here, this is the lowest finish time, 500. This corresponds to flow 4 packet number 12. So that is the one that goes out first, right. So next will be 666, right, which corresponds to 8200, okay. So the next one to go will be 1000, which corresponds to 5200 and so on. So this is how the packets will be sent out using WFQ. So WFQ is complex because there may be not just 1 or 2 flows, but hundreds to millions of flows that would actually be going in the network, and the line card will need to, your network line card needs to manage a Fifo per flow. So it can be a complex phenomenon, and the finish time has to be calculated for each arriving packet. So that also adds to the complexity, and the packets must be sorted by their departure time and they have to be picked out. So naively, even with M packets, the sorting time is order of log M. So these are some of the things that we have in terms of implementing WFQ. Okay. So, in practice of course it can be made of the order of log n for n active flows, but these are some of the complexities that we have with respect to implementing WFQ. The advantages of WFQ however are that it can be used to schedule delay sensitive traffic. Okay. So, delay sensitive traffic can be brought to the front of the queue in order to reduce response time and also share the remaining bandwidth fairly among the high bandwidth flows. So, getting close to the maximum fair share as such. So, this gives low volume traffic such as telnet sessions etc. higher priority over the high volume traffic such as FTP sessions. Okay, and it will give concurrent file transfers, balanced use of the link capacity, and automatically will adapt to changes in the network traffic conditions. Okay, so these are the advantages that we have of WFQ. Okay. So to summarize, we have looked at the different QoS scheduling algorithms. So we have looked at Fifo, first in first out, round robin, and how these are not fair, and we also looked at how to provide fair scheduling using bitwise round robin kind of techniques and how they are actually implemented using fair queuing and weighted fair queuing techniques. Okay. So this kind of the scheduling forms the basis for the packet scheduling algorithms that are used in the networks. Okay. So we need to understand this well. Thank you.